All right. There's like 6 prefatory comments I want to make, but I'm just going to try to cut it off. The one thing I will say is, despite the fact that you have yet another theoretical particle physicist who did a lot of things with simulation tools for particle colliders, this is not going to be the exact same talk. It's, in fact, going to be a very different talk. Is this not? This will, in fact, be the last thing you hear about quarks, just the picture on the slide. I'm maybe not, but we'll see. I also, just to say, I'm very confident about the first 2/3 of this talk, and then it gets very speculative, and a lot of it has adjusted over the last couple of days, so we'll see where that goes. The question I asked here, are we certain that protons exist? I know what I want the answer to be. I want the answer to be yes. I think the answer is yes, and I think we have the tools to say that the answer is yes. But my initial goal was just to sort of like gesture in that direction. I've attempted to at least motivate that a bit more strongly towards the end of the talk, but we'll see how well I've done the last couple of days. But the first thing I want to talk about is, before we get to the question of what are we certain about, in a certain sense, in the Thomistic epistemological sense, the first question is, before you can be certain about anything, you have to understand what the statement you're talking about is and whether that statement is true. So the first question is, what kinds of statements about nature should we expect to be true? Should we expect any statements about our study of nature to be true? Now, I'm not going to go into super skeptical things here. As most contemporary philosophers of science dealing with this question do, they take for granted the physical world and certain like accessible aspects to the senses. I'll say more about that in a moment. But just to hint at the issue related to certainty, you don't have to go too far to see places where people have claimed certainty in ways that now seem very, very silly. And to pick one example, Einstein quotes a particular textbook that was published in 1902 by Orest Danilovich Khvolstin, a Russian physicist. And apparently it's an extremely good text, like 5-volume series of texts that like completely changed how Russians studied physics. But in his introduction, he says the probability of the hypothesis on the existence of this agent, namely the luminiferous ether, that with more tensile strength than steel and yet able to have any physical body pass through it, we are more certain about the probability of this hypothesis borders on extraordinarily close to certainty. And Einstein quotes this to point how much has changed just in a few years. So there's a problem or a worry about scientists making claims about certainty. We've been pretty bad at it in the past. So how do we know we're not just in the exact same situation that our forebears have been? On the flip side, in one sense, we might say like we should look to philosophy of science. Maybe philosophy of science has, just like mathematicians or just like physicists make a muddle of mathematics when they just apply it willy-nilly where they feel useful. Maybe physicists just make a muddle of philosophy, and the philosophers have a better sense of what's going on and can help clarify it for us. Well, the problem is that philosophy of science itself has been struggling with this and has its own interesting claims you could point to. And again, I'm picking now here on Auguste Comte, who's often considered the father of contemporary modern philosophy of science. And in his series of works on his positive philosophy and talking about astronomy, he says that he has this idea that astronomy is basically just a sort of advanced version of geometry. And ultimately he says, our knowledge concerning their gaseous envelope is necessarily limited to their existence, size, or refractive power. We shall not at all be able to determine their chemical composition or even their density. I regard any notion concerning the true mean temperature of various stars as forever denied to us. Maybe 2 decades later, I guess, we had figured out how to measure temperature through spectroscopy, and a little bit after that, we're already applying it to stars. And as you saw from Dr. Kim's talk, we know a heck of a lot more about stars than just what direction they're in. So philosophy itself has struggled with this, and I want to focus in on one particular aspect of this question, which centers around the theme that we heard a little bit about from Dr. Duran yesterday, about this notion of scientific realism. So I want to just try to define this term, and to do that, I'm stealing what I find to be a helpful definition from Anjan Chakravarti, a contemporary philosopher of science, and in some ways, of contemporary philosophy of science, the person I'm going to most directly engage with because I think his ideas are very interesting and helpful. So if you start reading the literature on this, the definitions of scientific realism are about as broad as the number of people who have written definitions on scientific realism. But he tries to sort of hone in on this and points to three aspects about which scientific realists, broadly speaking, are realists. First, ontologically. Scientific realism is committed to the existence of a mind-independent world, or reality. Second, realist semantics implies that theoretical claims about this reality have truth values and should be construed literally, whether true or false. And I'll say a brief bit more about that in a moment. Finally, epistemologically, commitment is to the idea that these theoretical claims give us knowledge of the world. Why is there a difference between the semantics and epistemological? I'll say that in a moment. And this is predictively successful, that is, predictively successful, with his own caveat, mature, non-ad hoc theories, taken literally as describing the nature of a mind-independent reality, are, again, his caveat, approximately true. Roughly speaking, the things our best scientific theories tell us about entities and processes are decent descriptions of the way the world really is. So, if that's the definition of scientific realism, why not be a scientific realist? I mean, in some sense, that's a sort of like rough approach that a lot of people have when they think about the sciences. What reason would people have to not be a scientific realist? Well, there's two main arguments that are put forward. There's a lot, but here's the two central ones just to motivate briefly. The first is roughly called the pessimistic induction, which basically says, well, just look at the history of science, roughly what I was starting with. So here's just a particular list that comes from Loudon in the 1980s. Here's a whole list of scientific theories that people were really, really confident about that said real true things about the world, none of which we believe anymore. So the crystalline spheres, humoral theory of medicine, caloric heat, vital forces in physiology, et cetera, et cetera, et cetera. And, you can find other examples of this too. The other, again, which I'm just going to note on and briefly, is roughly the idea of underdetermination of theory. And I'm going to sort of summarize this in one slide. If we've seen versions of this in various places, right? So if those points of data are observations, there are different ways you could say what your model would be, or what the model to fit that data would be. If those are the only observations you have, you could say, well, maybe it's a linear plot and try to find the best line. Or you could get like a 25th order polynomial and apply it to it and see how you do. And in one sense, if both theories properly approximate the data, how can you determine which one is better? Sure, you might like simple theories, but why the heck should nature be simple? Why doesn't nature use 25th order polynomials? Why doesn't nature use, why even polynomials? Why stop there? So this is a worry about the fact that the particular mathematical formalism that we love is almost certain, like it's one among many of the mathematical formalisms that you could in principle apply. And there's stronger and weaker versions of this. Why the heck should you believe that this is the right one? So there's both a kind of like historical worry and then just a contemporary worry of like, look, there's just only finite amount of data. How can we possibly know that we have that we're on the right track? Okay, that's the motivation for not being a scientific realist. But then there are lots of different ways to not be a scientific realist or to be an anti-realist. And roughly, you can kind of tabulate them helpfully, as Chakravarti does here, based on which of the three questions he asks do you reject: the ontological, the semantic, or the epistemological. Starting at the bottom, you can go, you can go full on idealism. Why is there a real world at all? It's all in my mind. I mean, not all idealism is solipsistic, but basically you could just deny the existence of the real world. Very few contemporary philosophers of science go that far. Moving up a bit, there's a certain form of instrumentalism where you say, no, okay, the real world exists, sure, but scientific theories are just a kind of tool we use to coordinate all of the actual observational data that we see. And so, insofar as scientific theories are saying something about the explicit results of experiments we've done, then sure, that corresponds to there's a literal connection there. But insofar as anything in the theory says anything beyond what we have actually observed, then we shouldn't actually trust the theory. That we should interpret it not as being literal, but just being some kind of helpful tool in the moment. And similarly, then, it doesn't give us any actual knowledge about the real world. Moving up a bit, you have logical positivism, which was the most dominant form, or the most common philosophy of science in the early 20th century, which, again, the ontological question kind of depended upon who you asked. There was a bit of agnosticism about that in many quarters. And they, again, have this particular issue on the semantic question. And a simplistic way of saying this is saying that, again, it's a more advanced form of instrumentalism to a certain extent, where they're saying, yes, our theories are there to help us coordinate our understanding insofar as they relate to our observational data. But they also then said any terms that don't explicitly refer to something that's observable, there has to be a particular constructive way of turning that language into language that reduces to specific observables. And insofar as you use words that do not explicitly, by some particularly linguistic method, reduce down to things that you can actually observe, it has no meaning. So this has major ramifications for metaphysics and theology that the empiricists were not very fond of. So they thought that we were getting at real truth, but we were getting at truth about what was, but that truth involved this sort of translation of any terms that don't explicitly involve observational data into terms that do, so that all terms refer to observational data, and therefore all terms have the possibility of being true about the real world. Again, you can just be the straight-up skeptic, where you said, sure, yeah, okay, that's great. The real world might exist, and, sure, why don't we read our theories true, but why should I believe this theory says anything about reality? Again, there's different versions of that you could be. Contemporarily, the most common form of anti-realism, or the most talked about, is this constructive empiricism, the work of Bas van Fraassen. And he kind of has a shift. For various reasons, the kind of logical positivist project, in a way that's actually quite respectable, it just, the practitioners of it realized that their very project failed. That this idea of linguistic translation, for various reasons, philosophically, didn't work. They weren't able to make all of these linguistic translations, and then the similar axiomatization of physics that they were hoping for didn't work. So in this case, then, what Van Fraassen does is sort of take that intuition but shift it. So he says, okay, we don't need to play any language games. We take our scientific theories as fact. So if our scientific theory is saying things about cells or molecules or electrons, fine, we just talk about cells and molecules and electrons. But we just have a certain understanding of what science is actually capable of doing. And the kind of epistemic value that science has is not to give us truth about unobservable entities. The only scientific value the only epistemic value that science has is to be well adequated to what we can actually observe. And again, there are variations on this that you could make, but it's a kind of hesitancy to say anything concrete about unobservable entities. And again, what exactly is the difference between an observable and an unobservable? That's a very good question. Broadly speaking, for Van Fraassen, the moment you're using any sort of instrument, you're now in the realm of unobservable. So observable is directly observable to your physical human senses. Unobservable is any sort of instrument. I'm sure there's 25 questions that come up about that, but since I'm just going to blow through that barrier, I'm not even going to worry. I want to be the realist. I want to say yes about everything. So how can we go about doing that? Well, there are various ways to be a scientific realist. Clearly, a bad way to be a realist is to take the current best theory of science and think everything it says is absolutely true. We've seen that that's not quite right. But there's a certain kind of skepticism with which we have to approach science. There are certain things about it which we should have confidence in. Clearly, it's working in some mode. And yet, certain kinds of things about which we should be skeptical. And where and exactly how to draw that line in terms of contemporary arguments for realism has varied. So the three kind of most common would be explanationism in a certain sense, which is, okay, those unobservable aspects of, so again, here unobservable means not something that's hitting my physical senses, that are indispensable for explaining the success of our theory, whatever you think success is, whether it's novel predictions, particular ways of fitting to data. Those are the things that we should believe in, and we distinguish sort of idle posits, these other parts of our theory that are not indispensable for these explanations, from the working posits, the one that actually do the work of explaining why our theory works. This is hugely debated about how exactly can you figure out from here, looking forward, which ones are doing the work yet. It's great to look back and say, oh yeah, we didn't need this part of our theory because this is the part that explained it, but looking forward, it's not always so obvious what's the working part and the idle part. A second form of this is called anti-realism, which again, in a very brief summary, focuses on the idea that there are just certain entities, things of some form, and again, what exactly that means is variations there, that we do stuff with, we causally manipulate. They not only impinge upon our detectors, which is like step one of causal interaction, but then we turn around and use them to do other things. Not only have we seen positrons doing things, but then we get positrons to do things for us, to poke other things. And insofar as we're able to causally interact with these things in such a complicated way, we should have confidence in them. But built into this, to avoid worries about pessimistic induction and aspects of the possibility of undetermination theory, is an explicit agnosticism about the details of the theory. So the rough idea is that even though the way that we conceive of what an electron is and does, or what a proton is and does, is very different from the people who were first discovering the proton, were conceiving of that, we can just set that aside. The change in theory doesn't matter. We've been poking the same thing the whole time, and that's the grounds on which we can build up our realism. We've been seeing electrons do things, and then using or seeing protons do things, or seeing DNA do things for decades now. And even if our understanding of the details has changed, that's not the important part. We can be anti-realist about that, skeptical about that. We're still working on the details, but the things we should have confidence in. Again, hugely debated for various reasons. The third, which will sound familiar because it sounds a lot like the conventionalism that we heard about from referencing Poincaré, and the practitioners of or proponents of structural realism explicitly looked to Poincaré as an inspiration. Again, there are probably some nuances and details of how there might be variations, and within structural realism itself there are variations. But this is the idea of focusing on the relations, particularly the mathematical relations or structure described in our best theory. So in some ways, it's sort of the inverse of the anti-realism. It's the thing we should be skeptical about is exactly what the things down there are, but insofar as we built up healthy mathematical relationships that undergird the observational patterns that we have, insofar as that mathematical structure is consistent across theory change, that the way that light was dealt with when you had in the time of Foucault, not Foucault, the way in which light was dealt with sort of before and after Maxwell, and even into today, there's consistency in those equations. That yes, caloric fluid doesn't exist, but the experiments they were running and the kind of fluid flow equations they were using, aspects of those carry over into contemporary understanding of thermodynamics. So the math is what's important. Don't worry about the things. What I find very striking is so Chakravarti, in his work on metaphysics for scientific realism, makes the argument that all of these other attempts are problematic for various reasons, and wants to propose a kind of middle ground in between them. And the thing that he uses as the kind of fulcrum for this, because he calls it the fulcrum, as we'll see in the next slide, are what he calls causal properties. So what does he mean by causal properties? He says that the first order's property, so this comes after a discussion of structural realism and an issue about the fact of, that was sort of asked in a question, it's okay, that's great if mathematical equations continue over, but if the mathematical equations don't actually link into particular things or particular first-order properties, I can write an equation for heat flow, an equation for certain kinds of electrodynamics, and they're going to be very, very similar. How do I distinguish which one goes where or why they're not the same? There has to be something about a first-order property of something that is grounding those relations. And so he argues that the first-order properties whose relations comprise concrete structures are what I will call causal properties. They confer dispositions for relations, and thus dispositions for behavior on the particulars that have them, why and how do particulars interact. It is in virtue of the fact that they have certain properties, and they behave in the ways that they do. Properties such as masses, charges, accelerations, volumes, and temperatures all confer on the objects that have them certain abilities or capacities. These capacities are dispositions to behave in a certain way when in the presence or absence of other particulars and their causal properties. So again, a lot more to be said there, but just for the sake of time, I'm going to jump ahead. So he has this vision of the idea that, okay, causal properties permeate reality, that like in his initial presentation of this, he's intentionally kind of agnostic about what exactly he means by that, in an attempt to be as inviting and open to people who might be squeamish about causal properties. May or may not be a problem in this room. But he tries to sort of specify that and clarify that as he goes, and he ends up in a particular place with it. But the first distinction that's important here is, so there's this image where whatever is going on in the physical reality is this interaction between causal properties. And there are particular relations that can happen between different kinds of causal properties. And these relations tend to follow these particular mathematical patterns, this particular structure. And so insofar as we're doing science, what are the things that we should the first ground upon which we should have confidence? It's causal properties, but not just any causal properties. He says that we need to focus on the things that we can actually detect. So in this case, he's kind of incorporating something of entity realism in. That it's not just, I found a causal property, therefore it's real. It's like, have I actually engaged with that causal property? Has that actually impinged upon some sort of instrument that I can use and talk about as being a detection? That I have something of, it's not just, so he conceives of this as there being, there are lots of causal properties in the world. Only some of them have been detected by us. And so there's this little Venn diagram down here. In our theories, there are lots of properties that we might put, like causal seeming properties we might put in there. But those, until we've actually detected them, those are what he calls auxiliary properties. And we're just not sure where on the Venn diagram they fit. They may actually be real causal properties that we just haven't observed yet. Or they may be some other aspect of structure that doesn't that doesn't actually latch on to something real, and there's some real causal property that these are hiding some way underneath them. So, for instance, right, the mass of the Higgs boson, I would argue, is a causal property that has existed for, stability of the mass. Like, presuming there's been a mass of the Higgs boson since the Big Bang, probably the same mass. But we didn't know what it was until July 4th, 2012. So it has always been a causal property, but arguably it has only recently become a detection property. So he says the advice for semi-realism gives us straightforward. Believe in the relations of detection properties as given in the minimal interpretation. And again, there's some work to be done on that. And treat anything that exceeds these structures with caution. So focus on causal properties and that we can actually detect, and the relations between them, and that's where we should have the grist for the mill for a robust and stable kind of scientific realism. And here's a kind of just again, sort of summary quote of why he thinks this is so compelling. Causal properties are the fulcrum of semi-realism. The relations compose the concrete structure, so the relations between causal properties compose the concrete structures that are the primary subject matters of tenable scientific realism. Insofar as it's true that certain mathematical patterns have continued throughout theory change, it's because these are the concrete structures linking together particular causal properties. They regulate, cohere, and form into interesting units. So we start with the properties, but we just kind of weirdly notice that certain properties seem to come together. That the mass of the Higgs boson seems to be, easier one. The mass of the proton seems to always come together with the fundamental electric charge. Or, okay, no, that's false. If you threw a couple other quantum numbers in there, it would be true. So we got to worry about the neutron. But there are just certain groupings of causal properties that come together, and you could talk about it at the level of physics, and arguably you could work your way up. There are certain causal patterns and properties proper to dogs that are different from those proper to an oak tree. And that's that there's a certain way in which we can identify individuals as having these collection of causal properties. The continuous manifestation of the dispositions they confer constitute the causal properties to which empirical investigations become connected. I just want to point out here, continuous manifestations of dispositions. He is explicitly saying that Hume is wrong about talking about causality, insofar as you want to talk about cause-effect as being cause first, effect later. He says you're misunderstanding how causes should work and how they very clearly seem to be working in scientific practice, that there is an interaction between coextensive, like temporal, two different causal properties are interacting over a period of time to bring about the various effects that manifest themselves. So the scientific realists then reach beyond what is observable, what directly hits our sense powers, to claim knowledge of certain unobservable properties first, then structures, and then particulars, and by doing so enter into the speculative water of metaphysics. Now, pause it for the Thomist here. He's actually talking about natural philosophy. Metaphysics has had a shift in terminology, but it's talking about what really exists. Okay, moving ahead. So what should a Thomist think about this? Just as a brief review to try and motivate this, again, what is the Thomistic picture of natural philosophy, of the natural world? Natural things, the world is composed of natural things. Natural things are substances, which are composites of prime matter and substantial form, as well as various accidents, some of which are proper accidents and some of which are not. So, for instance, just as they may or may not have come up, I don't think it came up exactly. The density of diamond is a proper accident of diamond. The mass and shape of diamond are not proper. Some diamonds are really big, some diamonds are really small. You can carve them and make the shape different. So all of those are accidents of, like, this particular diamond has a mass and a shape, but the mass of the diamond is not proper to it. The density, the hardness, the thermal conductivity, those would be accidents that would be proper to it. Certain accidents, certain accidents, certain subset of qualities of a substance are that by which it can act or be acted upon. These are where Thomists should be looking for causal powers. In a certain subset, not all, but a certain subset of the accident of quality. This is always going to be conditioned by quantity in the sense that qualities only exist spatially in a spatially structured space. So the quality will exist in a particular region. So quantity is going to be in the background there. But what's doing the work is the qualitative feature. And here I just quote from this extremely good book by Gloria Frost, who clarifies a lot of things about, even for me, about just confusion about how Aquinas thinks about causation and causal powers. So Aquinas thinks that instances of per se efficient causation include each of the following: an efficient cause, which is also an agent, an action which the agent performs by its active power due to a natural inclination for an end or a goal. So we're talking about a particular thing with a particular power performing an action that has a certain teleology to it. So while we're, in one sense, focusing on efficient causality, in the background, there's formal causality and final causality here. Efficient causes only ever act for an end. Things only act through what they are in acts, how they're formed. But that's not the whole story, because something in action always acts on something else. In addition to the four features just listed, all of which pertain to the agent, instances of efficient causation also include something upon which the agent acts, namely a patient, with an appropriate passive power, and a motion or change which the agent causes and the patient undergoes as its passion. Now, just to be clear here, ultimately speaking, the efficient cause here and the agent and the patient are going to be substances, but it may not be different substances. So this could be happening inside of me, where there's a part of me acting on another part, and I can talk about one part of me being the agent, another part of me being the patient. So substance is in the background here, but in some ways it's very much in the background. The key here is actually accidental form and qualities. Okay. So, but in this formulation, right, we start with prime matter and substantial form. And so there's that immediate question, well, like, what kind of thing are we talking about? What's the thing we're dealing with? The problem is, I think a lot of times our Thomistic intuitions about this are a little bit malformed, where we all know that all knowledge begins in the senses. And we all know that there is no sense power by which we sense substantial form. But a lot of Thomists kind of talk as if we had a sense power by which we immediately sense substantial form. That I look at a tree and I just get the tree form immediately, the substantial form of tree immediately. And that's just not how Aquinas thinks that epistemology works. We get accidental forms, we sense them through our senses, we reconstruct them in our imagination, and then we abstract from them and reason to what substance may or may not be there. So our senses are acted upon by some sort of sensible power, particular accidental qualities. We abstract various kinds of accidental features. So we have like natures of particular accidents, and sometimes can reason to the substances. Just sort of two quotes to motivate this for Aquinas. It must be said that because substantial forms in themselves are unknown, but become known to us by their proper accidents, substantial differences are frequently taken from accidents instead of from the substantial form directly, which become known through such accidents. So it's through accidents that we reason to what substances are there. In the same thing, and this is a different quote, in both of these quotes he's actually thinking about trying to understand spiritual beings, but he's talking about just how weak even our understanding of physical beings can be. The same thing, moreover, appears quite clearly from the defect that we experience every day in our knowledge of things. We do not know a great many of the properties of sensible things. We don't always know what all the proper accidents of sensible things are. And in most cases, we are not able to fully discover the natures of those properties that we apprehend by the senses. Now, there's a certain humility built into this that I think is, in one sense, healthy, but I think where Aquinas drew the line is probably wrong for various reasons, and that gets into the fun topic of occult powers, but we're going to move on. So a rough argument of, okay, in the order of discovery, when I'm going out into the world and trying to see what's out there, I mean, and this is the pattern, this is always the pattern, not just in science, but since it is always the pattern, it's also the pattern we should expect when we're doing science. The first thing a Thomist should be realist about are sensible causal powers. The things that I'm seeing and are hitting my senses. That's the first thing. Before we can be realist about anything else, we have to be realist about the fact that I'm actually seeing something, feeling something, hearing something. We can recognize, recognize other unobservable, non-sensible causal powers in the sensible effects, most often some kind of motion, that they bring about. For instance, the fact that a magnet attracts iron. I can't sense magnetic field, but I can see the effect of magnetic field in certain circumstances by the motion it causes in other things. We use the effects to group various kinds of causal powers, hopefully carving nature at its joints, hopefully distinguishing real differences between this kind of causal power and another. Always careful that maybe we're missing the joints a little bit. We notice particular collections of accidents grouping stably in some region, and we reason to there being an individual thing. Thing star, we'll come to that in a minute. So in that place. So that grayish, furry, heavy, four-legged thing, that seems to be a pretty stable thing. I've seen a lot of those before. We have a name for them now. They're squirrels. In comparing distinct but apparently similar individuals, we notice certain common groupings of particular accidents across all of them and judge that they are proper accidents. Like this squirrel is really fat and slow. That squirrel is really lean and runs really fast. But all of them have bushy gray tails and four legs. Like there's ways in which we can sort of see similarities and reason to certain things being proper to them and other things being less so. In cataloging the proper accidents of particular groups of things, we begin to uncover something of the natures of the various kinds of things involved Again, hopefully carving nature at its joints. And just as a star, like not all of the things that we first grasp onto will necessarily be individual substances within a unique substantial form. It's not hard and not uncommon to focus on a part of a substance. I can say lots of things about my eyeball, but for a Thomist, an eyeball doesn't have a substantial form. It's a part of me. That doesn't mean I shouldn't see that there are particular proper aspects of my eyeball that are very different from the proper aspects of my spleen. And so like we can still use the same kind of language without necessarily without worrying about what the substance is immediately. Eventually we might want to get there. In the same way, it's also very easy to group lots of things together. Here in my class, I would show a picture of a big forest of trees, like, oh, look at all these trees. That's great. Turns out, all connected by the root, genetically the same, one big, massive tree organism. Great. Okay. So distinguishing when we're looking at one thing or multiple things is not, it takes an effort to get there. Again, there's no magic immediate access to substantial form that we have. We have to work through the sense data to get there. So looking at this together, there are just certain details about how Chakravarti explains causal powers ultimately that are problematic. He wants to explain that the essence of a causal power in a certain sense is just all of the possible ways that it could possibly interact with any other thing. It gets into contemporary philosophy of science and and possible worlds, ontologies, things. So, but for the Thomist, that's frustrating because he's defining the essence of something in terms of its potencies instead of its actualities. The Thomist is going to have a different story for what makes a slightly different story for what makes this particular causal power the kind of causal power it is. And so this leads to other sort of downstream diverges. His intuitions about natural kinds are different, and a few other things. And the Thomist is going to want to say a lot more than Chakravarti is willing to, beginning with distinguishing active and passive powers, which I brought up, moving on to speculate about parts and wholes. Where exactly are these lines? Substances, substantial forms. For instance, are blood cells substances or part of a substance? What tools do we have to reason about that? But insofar as we are asking just the question, what aspects of our scientific theories we should have most confidence in, we just do share a very common approach. The kinds of causal powers distinguished by, identified by their relationship to, and the way they interact with other causal powers. That's how we like both Chakravarti and a Thomist would argue that's how we discover that there are causal powers out there, or particular kinds of causal powers. Again, the Thomist is going to want to say more about the notion of accidental form and actuality, like why we identify this causal power as another ontologically. But in terms of discovery, how do we figure out there are magnets? By putting magnets near iron and seeing the causal effect they have. And then consistent groupings of causal powers that tend to come together in individual entities, again, holding off the question about further substances. The Thomist wants to get there eventually, but insofar as we're dealing with very speculative aspects of contemporary science, we need to be patient about that. Okay, so that was intended to be roughly 40 minutes of the talk, and it is. So I'm a little behind where I'd like to be, but I do want to move into the question of scientific demonstration, because insofar as the grounds for what we should have confidence in, it's just to back up. As you notice in that quote from Chakravarti, he talks about approximate truth. There is a great hesitancy in most contemporary philosophy of science to make the argument that we have absolute truth. Why is it? For various reasons, that came up in Steve's talk about, the standard model is great and all, but we just know it's not right yet. Like, we don't have all of the answers, so how do we know we have truth yet? And here, I think, is where the Thomistic instinct shifts. Because insofar as we're able to ask particular questions about particular kinds of things, we can argue that we are actually getting to something of truth. And if you're starting to make statements that we believe to be true, that we have reasonable opinion for thinking are true, it's possible to ask the further question: do we know that? Do we not just think that that's true or believe that's true, but do we know with certainty that is true? And it turns out the very tools by which we're talking about discovering the kinds of things that we might want to claim are true in our physical theories is the very tool that Thomists want to use to argue for when we have knowledge that is certain about various entities, through the causal powers, through the causal properties that are engaged. With this, though, there needs to be a little bit of lowering expectations, because certainty is a loaded term. Certainty for the Thomist natural philosopher is not Descartes' certainty. It is not. It's not certainty. It's not even the certainty of mathematics. It's not even the certainty of metaphysics. There's a kind of certainty proper to reasoning about the physical world. Insofar as I know lots of things about the physical world, I might predict what might happen, but from a Thomistic perspective, we can never be absolutely certain about what's going to happen in the future. So that there's certain limits on the kinds of certainty we can hope for, the kinds of certainty we want to say. As a helpful just analogy on this, Aquinas thinks that we can make demonstrations in moral philosophy. Not a lot, but a few. But that is not a claim that, okay, given the situation, if I do this act, this is the outcome of the act. No, the kind of certainty you have in moral proper questions is, given this situation, this is the right thing for me to do in this moment to be a virtuous person. And I can be absolutely certain that this is the right thing to do, very, very open to the fact that this might lead to my very death or something else like that. So the kind of certainty, what we should have certainty, is going to look different in the philosophy of nature. And so we need to build up slightly different instincts about what we mean by certainty. And in one sense, I would argue those instincts are already built into the way that we tend to talk about science. So I'm going to try to run through a couple of concrete examples, and it's going to be quick. So I'm going to start with a classic example and then try to get to protons. We'll see how far we get. So we'll start with phases of the moon. So this is a classic example from Aristotle. The moon is a body that waxes and wanes through crescent phases. And if insofar as you understand how spheres work and how optics work, it's clear that a body that exhibits these sort of waxing and waning must be a spherical body illumined by an external source, namely the sun. The moon is a body that waxes and wanes in a particular way. Therefore, the moon is a spherical physical body illumined by an external source, namely the sun. Again, this is using mathematics in its argument, but it's a quantity of a physical object, and so it's saying something about the physical thing. This is an a posteriori demonstration. This is reasoning from an effect to a cause. So we haven't quite gotten to the really high level of demonstration that Thomists want, but it's a kind of demonstration. And notably, there are certain suppositions involved. We're presuming light travels in straight lines. We're presuming certain truths about the nature of light. We're also generally presuming the fact that the moon's not going to explode in the next 5 minutes. There are certain aspects of stability of nature that are suppositions in the way that we're approaching this question. But insofar as we take those seriously, we do know that the moon is a sphere. So this is an example that Father Wallace uses in a really kind of awesome paper called Some Demonstration Philosophy of Nature, or Science of Nature, where he lists like 35 different things that he thinks are demonstrations. Here's another demonstration. It's extremely similar to the last. A spherical body illumined by an external source, the sun, is a body that waxes and wanes through crescent phases. The moon is a spherical body illumined by an external source, the sun. The moon is a body that waxes and wanes through crescent phases. This is, in one sense, the same argument, right? And yet we've flipped the middle and the predicate in such a way that, having proved that the sun is a sphere, having knowledge of the fact that the sun is a sphere, and understanding details about projective geometry, we can now explain why the crescent phases of the moon are what they are. Again, it's the same kind of argument, and yet, insofar as this actually works, there's a lot of work between step 1 and step 2. Just to say, like, if you want to read more about this, another work by Father Wallace, where he is explicitly quoting constantly Galileo, because this is the logic of discovery that Galileo is using in all of his scientific works. Galileo is explicitly drawing on Aristotelian demonstration as the mode for arguing for causes in all of his astronomical works. In fact, this same structure is the way in which he argues for the fact that the moon is not a perfect sphere, that it has particular structure to it. He proposes an argument about there being shadows and lights that he sees on the moon through a telescope, and reasons to the fact that there must be mountains, and he can actually measure the distance to the mountains based off of his understanding of projective geometry. So he can first argue to the fact that there must be some sort of structure on the moon, and then through a process called demonstrative regressus, which is complicated and still working through myself, works out a way in which he has confidence that I now know why it is that the moon has this particular structure when I look at it. Great. Now getting to the harder parts. Millikan oil drop experiment. There's a way in which we can formulate the logic of the Millikan oil drop experiment in this demonstrative mode, right? The electric charge, an electric charge that varies in discrete steps from some minimum value, is caused by unit electric charge. That electric charge, when we do the experiment, that is what we see. Therefore, the electric charge on a minute oil drop is caused by unit electric charges, namely that we now call electrons. Or, well, the name was out there. But again, a couple things to note. We're not saying we know everything there is about electrons. We're just saying, okay, there's this mathematical pattern in how charges work, where there's discrete steps. It seems like that there has to be something like a unit to explain those discrete steps. This has lots of suppositions built into it. I mean, this is a horribly complicated experiment that has all sorts of suppositions involving Stokes' law and drag theory. In fact, Millikan gets it wrong. He actually is off on his calculation of the electric charge because he has the wrong value for the viscosity of air. That said, the overall pattern, the discreteness of the pattern, is still true. The thing I want to argue about here is, again, garbage in, garbage out. The goodness of your demonstration is only as good as the goodness of your premises. And insofar as we can and should use experimental tools and experimental observations as premises in these kinds of demonstrations, it's going to have built-in uncertainty and a built-in possibility of systematic error. So there's the kind of certainty we're finding is not the certainty by which we know for a fact we've gotten all of the details right, but that given the complex combination of causes that go into a particular situation, we have great confidence that we have the right explanation for why these phenomena happen. Okay, just to jump ahead, there's a version of this you could do for the proton. Here, I mean, there are different points where you can talk about interesting discoveries in the proton. One of which is you can bombard nitrogen, like pure nitrogen, with alpha particles. So you're talking about helium atoms and or helium nuclei. They didn't really know that. Your helium nuclei and nitrogen nuclei, and suddenly you start seeing all these hydrogen ions pop out. There's no hydrogen in the system to start with. Where's all this hydrogen coming from? The idea that, the hydrogen ion must be inside of either the alpha particle or the nitrogen. Again, lots of suppositions there, and yet it's the right conclusion to come to. And there's a certain, presuming the suppositions are right and presuming the logic of the experiment, it's the result is true, and we know that certainly. Okay. Ideally, you can then flip this around and say, now, not only do we have knowledge of the fact that protons pop out now and again, but we can actually have such detailed understanding of the charge and mass of the proton and the way that it puts energy into a physical system that we can actually shoot it at things to kill them. So we can use the proton to deposit energy into a tumor to kill it in a very controlled and particular way, and we're not confused about what's causing the death of the tumor. We know for certain it is this beam of protons that is causing the death of that tumor. I think that's intuitively present in the way that scientists think about and talk about things. And I think this is the right kind of approach for making sense of that, with an understanding of the complexity that goes into all the conversation we've had about mathematical uncertainty, worries about statistical uncertainties, but that we can formulate why it is that science does approach things like truth and does approach things like certainty. That gets better and better the more we understand and clarify our suppositions. Gone over, stop there. I'm sure everyone is completely convinced. Thank you very much.
Time for questions.
So in the last example of the proton beam, how do you see, what type of language should we be talking about? If you could then ask, well, what's It's killing your cells by damaging the DNA or just frying them with heat, and this never-ending quest
Sure.
to find all the things mediating, the
Yeah.
whole mediating chain.
No, that's great. No, so like insofar as I am confident that protons exist, I'm actually kind of squeamish about quarks. Like, I'm not claiming we know everything there is to know about the proton. I'm not claiming that we have figured out, like, that we know for a fact that the proton is exactly this particular combination of quarks. It probably is. I'm just saying that for a point of argument. But perhaps there's more structure down below that explains that, like, maybe there is some structure and combination of relations of lower causal powers that explain why electric charge works, that we just don't know about. We just haven't gotten there yet. Maybe there are strings down there. Who knows? But the certainty is not about everything protons do or could do, but insofar as we have actually engaged particular causal properties that we group together as this individual that is the proton, we have confidence in that. And we have, I would argue, certainty that it's not a mystery when you turn on a proton emission therapy machine. It's like, oh my gosh, the tumor died. Like, you understand what happened, and you're not looking for something else to explain it. You know with certainty what caused that. Again, if for instance the tumor doesn't die, if for instance some other part of the body starts getting hurt, then suddenly you start asking questions. What's going on here? What went wrong? Like, something about this pattern didn't quite work. Maybe, most likely it's a mistake in the setup. Maybe we realize that there's something more going on in that interaction that we didn't quite understand. We've tested it in these ranges, but as we extend beyond it, we're not so sure. This is where the difference between our understanding of the proton and the certainty of luminiferous ether comes in, right? There was in no way any actual causal interaction with anything like a tension of a luminiferous ether, or anything like a viscosity of luminiferous ether, or anything like a continuity of luminiferous ether. All there was interaction with phenomena of light that we saw were waves, and the presumption that there must be underlying it some kind of physical medium. At various points, particulate, other times continuous, depending on who you asked. And you just end up requiring it to, if you presume that, you get all these other causal, like seemingly causal properties, having a particular tension, having a particular viscosity. But it turns out that none of that is actually there. And we went beyond what was actually detection properties, reasoning beyond it. I would argue that we have lots and lots of detection properties of the proton in tons and tons of situations, from particle physics to condensed matter physics to quantum chemistry, biochemistry, like even biology in certain realms, that there is just this, that there's a kind of certainty for not everything about the proton, but a lot of things about the proton. Yeah. Yeah.
I just wanted to, if you could narrow down a little bit better what kind of certainty we're talking about. So by contrast with something people sometimes call moral certainty.
Yeah.
So Descartes, for example, gives the exact, I think it's an example like he's morally certain that there's a city called, that Rome is a city.
Yeah.
Because lots of people have been there, and
Yeah.
it couldn't be, society would have to be radically different from what you think it is.
Yeah.
Or people would always be lying to you about
Right.
Rome existing. So that's a moral certainty that depends on the social nature of
Yep.
humans.
Yep.
This, what you're talking about, is a kind of maybe physical certainty due to what we see when things are not impeded, or when things are. And then this actually makes me wonder whether actually it still falls under moral certainty, because all of these things that you're talking about, the different properties of protons, are all reported to us by different scientists who have done different experiments, and we haven't done those experiments ourselves.
Nope, exactly.
So I guess, with which kind of certainty do you think it is that it's protons that are causing the tumors to die or whatever?
So there are two ways to talk about certainty. Again, good distinction to make. There is a way in which a particular logical argument can be demonstrative, such that, if the premises are true, the conclusion will necessarily follow. And so if it is the case that those premises are true and that demonstration is possible, then that conclusion is necessarily true. and is certainly true. That's different from me having worked through all the details to understand that that demonstration is certainly true. So as a theoretical particle physicist, I would argue I don't actually know that protons exist because I never actually do an experiment to touch anything. So I've done a few things that I think give me enough credence to have confidence in it. So there's a certain sense in which this is, yes, there's a social and communal aspect to the building up of what a good demonstration for why we, in a collective sense, should have confidence in this, and some subset of people would be able to actually understand the premises, have experience the observations, understand the premises, and understand the proper suppositions, such that they have that certainty. A lot of us are going to be accepting it on authority, but that's different from just saying like it's all socially constructed. It's rooted in the fact that there is an ontological connection between cause and effect that we are making explicit in these kinds of demonstrations. That is really in the world. And it's insofar as we're doing good science that we're able to sort of draw out what those cause-effect relationships are, such that it is, at least in principle, possible to have certainty about the truth of the conclusion. If we don't know what those cause-effect relationships are, no one is going to have certainty about it. And if we're wrong about those cause-effect relationships, which again, as with any demonstrative process, it's hard, and we're human beings, and it's possible to make mistakes. This is another weakening of, and kind of lowering the bar of certainty, right? So, in a context that's what we're familiar for Thomists, right? God exists. There are logical arguments for that God exists. We can prove that God exists, but it's really hard and takes a long time. And if you try to do it purely by reason, there's a good chance you make a mistake. I'd say the same thing about science. That doesn't mean that it's not certain that God exists, even if lots of people deny him, right? So there's a difference between the ontological certainty rooted in cause and effect that we can make manifest in producing a good demonstration, and then the actual process of learning how to understand that demonstration and achieve that certainty, like that rational certainty on your own. That's always going to be for a smaller community, for any field, for any science. And most of us are going to accept it on authority.
So just to quickly, maybe you could call it, is there a name for this? Is it physical certainty for...
Yeah, so Aquinas just talks...
Regularities of causal dispositions that you see due to the natures of things? Or...
No, that's exactly... Yeah, so I'm trying to remember if Aquinas explicitly uses that term, but there just is a different kind of certainty for metaphysics, mathematics, philosophy of nature, moral philosophy. They're all demonstrations. They all follow the same logic, similar logical patterns, but the notion of certainty proper to them is different because you're talking about different objects. Yeah.
All right, let's thank our speaker. If you have pressing questions for Father, don't worry, you can get them in about 12 minutes. So return back here by 2:45 and we'll have our panel discussion.
This is a long part one is part two is something I wanted to do but this is a long term. I'm convinced